Hello, everyone. Here's our lecture on solutions. So we kind of started this lecture last night when you watched the slides, the video about aqueous systems. And so today we're going to expand on that a little bit, talk about solutions and how we measure concentration. So one of the first things that we need to make sure we understand is this term solubility. So solubility is a characteristic of a chemical or of a compound. Um, and that means that it's different from one compound to another. Um, the solubility means the amount of a substance that can dissolve into a given solute at a given temperature to make a saturated solution. We're going to see what saturated means in just a sec, so set that aside for now. Amount of substance that can dissolve. So we're talking about the solute. How much of the solute at a given temperature, because it changes with temperature, as we'll see in a second, can we dissolve into our solvent, and it'll change from one solvent to another, to produce a saturated solution. The example that we can think of is tea. Again, I think I used that as an example the other day. If you have a cup of hot tea versus a cup of iced tea, which one do you think you can dissolve more sugar into? Because people like to put sugar in tea. I don't, because I don't even like tea, whether it's hot or cold. I don't drink it either way, but some people do, so I understand. Um, so if you're dissolving, or if you're putting sugar into your tea, you may have experienced the fact that you can put a lot more sugar into a cup of hot tea than you can put into the same amount of cold tea. So if you have a cup of hot tea and a cup of cold tea, you can put a lot more sugar into hot tea. That's because the solubility of sugar depends on the temperature of the solvent. So warmer solvents can dissolve more sugar than cold ones. So let's take that apart a little bit. We'll sort of circle back to that in just a second after we go through the next slide. This term here, saturated. Let's see what that means. So there are ways to describe how much solute you have dissolved in your solvent, and we can kind of classify them with three terms: unsaturated, saturated, and supersaturated. Okay, so let's see what each of these means. Unsaturated means you have not yet dissolved as much solute as possible. It's not completely saturated. You can add some more solute and have it go into solution and have it dissolve still. So from an unsaturated solution, you can add some additional solute until you've um, reached the saturation point where any additional solute doesn't dissolve. And again, back to this sugar and tea example. If you keep putting sugar into your iced tea, particularly, it's easy to see with iced tea, um, eventually you get to a point where you add more sugar and it doesn't dissolve anymore. It just floats down to the bottom of the glass and sits there as a lump of solid sugar still. So you would say that you had saturated the tea with sugar because you can't fit any more dissolved sugar into it, okay? So that's what saturated means. The solvent cannot hold any more solute. But if you trick things the right way, for example, if you warm up your tea and dissolve more sugar into it, because a warm solution can have more solute than a cold solution. If you warm up your tea and dissolve more sugar in it, and then under the right conditions, if you carefully cool your tea down, you can create what's called a supersaturated solution where you can think of this as though there's more sugar dissolved in the tea than there really should be, right? Because you change the conditions, you change the temperature, you create a warm solution, you dissolve a lot of sugar in it, and then you carefully cool the solution down. The sugar stays dissolved, but it's more sugar than should technically be appropriate. You know what I'm saying? It's more than your tea should be able to hold. That's called a supersaturated solution. All right, so you're going to want to know the difference between these three terms. So we kind of hinted at this. Let's look at the factors that actually affect solubility. We've mentioned one already, temperature. So as temperature goes up, the amount of liquid or solid that you can dissolve in a liquid increases. All right, so remember, kind of spinning back to yesterday, You can have a solution can be a solid dissolved in a liquid, like the sugar dissolved in tea, or it can be a liquid dissolved into a liquid, or it can be a gas dissolved into a liquid, or it can be a gas dissolved into another gas. All five of those possibilities exist. All right, um, so some of them, different examples will occur to us as we go through here. So as temperature increases, the amount of solute that is a liquid or a solid that you can dissolve in a solvent generally goes up, like the sugar in the tea situation. However, the solubility of a gas in a liquid decreases. So think of your, actually the example I'd like to give is of a soda, a can of Coke or Pepsi or whatever. There is more carbon dioxide, carbonation, in a cold soda than there is in a warm soda, because as the soda warms up, the solubility of the gas in the liquid decreases and the fizz comes off the soda, and there's less carbonation left in the liquid because the warmer solution cannot hold as much gas. So the solubility of gases will go down, but the solubility of liquids and solids goes up as temperature goes up. We have to mention pressure. We haven't really talked about pressure much because we haven't really got to our gases unit yet. That's coming up very soon. Pressure has an effect on gases, all right? And as pressure goes up, it doesn't have much effect on liquids or solids because their pressure in general doesn't affect those states of matter. But for a gas, if you increase the pressure, the amount of gas that can be dissolved into a liquid goes up. So the solubility of a gas will increase as pressure increases. The solubility of a gas will decrease as temperature increases. See how they go in the opposite direction there? There's another factor that affects solubility that we need to discuss, and that's surface area. All right, so let's go back to our sugar example again. If you had sugar, you know what a sugar cube is, right? I don't know that you see those so often anymore. It's a cube of compressed sugar, and that the people used to put those into their drinks, as opposed to like sugar that is ground up and loose, like you find in the kitchen, right? That you bake with or whatever. Okay, so the surface area of a cube of sugar is small compared to that same amount of sugar that's all ground up. All right. So as the surface area increases, the rate of solvation, so how quickly the solid, the solid dissolves into the liquid, that rate increases as the surface area goes up, but it doesn't affect the solubility. So you can the amount of solute that can be dissolved is unchanged by surface area, but how quickly it happens will change. As you have more surface area, you have a faster rate of dissolving. So that's what we're saying by this point here. The rate of solvation, or how quickly the solute becomes dissolved in the solvent, increases as you get more surface area. Okay? Okay, one of the key pieces that we need to get out of our solution chemistry unit is how we measure concentration. So there are 4 ways that we measure concentration. By concentration, I mean the amount of solute that is dissolved in a solvent. And here are the 4 ways that we measure it. One is called molarity, one is called grams per liter, one is called percent composition, and there are 2 flavors of that. And then the last one is parts per million. All right, so we're going to talk about each of these 4 ways to measure concentration. We're actually going to start with the easiest, grams per liter. And I bet just by looking at the name of this, you can figure out how you do it. You take the grams of the solute and you divide it by the liters of the solvent. Grams per liter, that's that concentration. That's one way of measuring concentration in solution chemistry. Grams of solute over liters of solvent. So an example might be you have 1.5 grams of sodium chloride dissolved in 780 milliliters of water. What is the concentration of sodium chloride? Why does my computer keep doing that? Okay, there. So how do you solve this? Well, we're going to put grams of solute, which is right here, over liters, not milliliters, of solvent. So here's the solution, 1.5 grams of sodium chloride over 0.78 liters of water. Do you see how we did that conversion? 780 milliliters is the same as 0.78 liters, all right? So you put 1.5 over 0.78, the answer you get 1.9 grams per liter. That's the concentration in grams per liter in this situation. Kind of straightforward, I think. Good. The second way that we measure concentration is called molarity, and this is far and away the most common in chemistry. So you're going to see this one more than any other type of concentration measurement. And we actually have run into this already when we talked about our hydrochloric acid that we were using a couple days ago in the lab. It was a 1 molar HCl, or 1M HCl. This is the abbreviation for molarity. Notice it's a capital M. Not a small m, but a capital M. Okay, capital M is the abbreviation for molarity, and the definition for this unit is moles of solute over liters of solvent. So kind of like the previous one, but a little different. All right, so let's see how that plays out. If you had a solution where there were 4 moles of lithium chloride dissolved in 5 liters of water, what is the molarity of the solution? Okay, how do we do that? Well, we take moles of solute over liters of solvent, and so you end up with 4.0 over 5.0, and the answer is 0.8. Here's the units, capital M, that stands for molarity. So 0.8 M lithium chloride. Now let me give you a quick note about what we call this unit. It gets a little bit confusing because it has a couple of different names. Capital M is the letter that you write as the abbreviation for this unit. What we are measuring is called molarity, which is the moles of solute over liters of solvent. But when you say it, you call it molar, M-O-L-A-R, molar. So this is called a 0.8 molar solution of lithium chloride, or 0.8 molar lithium chloride, M-O-L-A-R. That's how we kind of read this abbreviation. 0.8 capital M stands for 0.8 molar lithium chloride. Okay? So I want you to practice one, because this, like I said, molarity is the most important in our chemistry world, so I want to make sure everybody's really comfortable with this. If you had 10 grams, notice that's not moles, that's grams, of sodium iodide dissolved in 5 liters of water, what is the molarity in moles per liter of the solution? Now, the definition of molarity is moles over liters, but notice that you've got grams. I want you to work this out, so I'm going to give you a second. You can pause the video, work it out on a little piece of scratch paper, or write in your notes, or whatever, but I want you to work this out. I'll wait. Okay, we're back. So here's how we do this. The first step is to make sure you convert these grams to moles, right? That's important. So we have, stop it. We have 10 grams of sodium iodide right here, and we use the molar mass, 149.9 grams per mole, to convert this to a moles of sodium iodide. All right, and then we take to find the molarity, we put moles over liters, so 0.0667 moles of sodium iodide over 5 liters of water, which, if you do the math, should convert to 0.013 molar sodium iodide. I hope that's the answer you got. That's the answer I got. Okay. Our third type of concentration that we're going to talk about was percent composition. There were 2 flavors, I said. One is called percent by volume, and the other we'll get to in a sec. Percent by volume is abbreviated with this very strange looking abbreviation, percent V over V, and it's defined as the volume of the solute over the total volume of the solution. All right? So notice that you're talking about a volume of solute, not a mass, but a volume. This is common in measuring the concentrations of liquids dissolved in other liquids, so that you can have a volume of the solute over the total solution volume. All right? Times 100, of course, because it's a percentage. All right. Not super common. I'm going to do this a lot in our chemistry class. You'll see these from time to time out in the world, but um, we don't do these a lot in our class. The other flavor of percent composition is called percent by mass. And this is where you have the mass of the solute in grams divided by the total solution volume again. So it's similar to the sort of structurally to percent by volume, but instead of a volume of solute, we've got a mass of solute. And this is more appropriate for when you've got a solid dissolved in a liquid. Um, and here's the abbreviation, percent M over V. See the difference between these two? So percent by volume, percent by mass. Otherwise, they're very much alike. The calculations are extremely simple because you either know the volume of your solute or the mass of your solute, and you divide it by the total solution volume. That's how you get percent by volume or percent by mass. Last one is parts per million. This one can be confusing because of what the way the unit is defined, and so we're going to spend a minute talking about that. This is a common measurement in sort of ecological or environmental science kinds of applications, like when you're measuring contaminants in the atmosphere or contaminants in a lake or something like that. You'll often hear them measured in parts per million. And so we want to make sure we know what that means. Here's how we get there. It's defined as grams of the solute over millions of grams of solvent. Millions of grams of solvent. The idea here is that you have something that's really, really dilute. Um, the the solute that you're talking about, there's really not very much of it at all compared to how much solvent there is. Okay, so instead of having just grams of solvent on the bottom, for example, which might have been a way to measure this, we would get a really, really small number. So um, instead, we put the grams of solute over millions of grams of solvent. And that gives us a kind of a more reasonable number to look at. Let's see an example, and maybe it'll help understand this. So DDT is an insecticide that is a common environmental pollutant, contaminant. And if you had a situation or you took a sample from a lake, for example, where there were 3 grams of DDT, this toxin, found in 2 times 10 to the 6th, which is 2 million grams of water, what would be the concentration in parts per million? Well, we want to put the grams of solute, which is 3 grams, and we want to divide that by millions of grams of solvent. Well, how many millions of grams are there? If I have 2 million grams of water, that means I have 2 millions of grams. So I would have 2 on the bottom. Let's see. I've got 3 grams on top from here, 3 grams of DDT over 2 million grams of solvent. So 3 over 2 equals 1.5. All right. So the trick to these is to working with parts per million is recognizing that the denominator is in millions of grams of solvent. So you have to kind of figure out, and this example is pretty straightforward, other ones might not be so straightforward. You have to figure out how many millions of grams of solvent you have. That's usually the hardest part in doing a parts per million calculation. Once you have nailed that particular piece, the rest is pretty straightforward. So those are the 4 ways of measuring concentration that we're going to be using in this class, and that's the end of today's lecture. We will be working with molarity in our molarity lab on Monday. Make sure you print that out, and I guess that's it for now. Thank you.